Greetings and thank you for joining me for our third unit here in our college algebra course. This unit we focus on exponential and logarithmic functions, and we'll see some of the applied situations that we can use both of these functions in. Now we're going to study inverse functions first because exponential functions and logarithmic functions are inverse functions, and so without inverse functions we can't have the discussions that we need to have in this chapter. So that's why we start, as we do a lot of chapters, with some basics and build ourselves up. We have a definition we need to talk about here, and this is the definition of a one-to-one function. A function f with a domain D and a range R is one-to-one if either when my inputs are different in the domain, the outputs are different in the range, or if the outputs are the same in the range, then the inputs have to be the same. Then the inputs have to be the same in the domain. Pardon that little interruption there by that window. Gotta love Microsoft Word, don't you? Now let's think about what the function does here. Okay, a function takes something from the domain of f and maps it to the range of f. So a gets mapped to f of a. Now we're going to show that the function f of x equal 1 over x minus 2 is one-to-one, or we're going to figure out if it is or not. I'm going to consider f of a, and I'm going to assume that it's going to be equal to f of b. So this is going to be 1 over a minus 2. This is going to be 1 over b minus 2. Now we know the 1's are the same, so that means all I've got to worry about is making a minus 2 equal to b minus 2. And we add 2 to both sides, a equals b. Thus, since if f of a equals f of b and a equals b, f is 1, 2, 1. Alright, now we want to see if f of x equal 3 is a one-to-one function. So again, let's consider f of a. Now f of a in this case is going to be 3. And let's consider f of b in this case. F of b in this case is going to be 3. So if we let f of a equal f of b, well, 3 equals 3. That's all well and good, but we have not shown that a equals b. We have not shown a equals b. Thus, f of x equal 3 is not one-to-one. Let's consider the function f of x equal 2x cubed minus 4 and see if it's one-to-one or not. Well, let's check this out here. F of a equals 2a cubed minus 4. F of b equal 2b cubed minus 4. So if we set f of a equal to f of b, 2a cubed minus 4 equal 2b cubed minus 4, 2a cubed equals 2b cubed, a cubed equals b cubed. And now, looking at a cubed equal b cubed, then we can take the cube root of both sides here, and we'll show that a equals b. So f of x equal 2x cubed minus 4 is one-to-one. And so you've got a couple discussion questions to look at and some homework to look at. Now another way that we can figure out if a function is one-to-one or not is the horizontal line test. Now before I go on, I want to talk about how the definition of a function is portrayed in the vertical line test. Alright, if we have a function, and let's come up here for just a minute and talk. If we have a function f of x equal, I don't know, 3x. It's going to look something like this. Now we know that the vertical line test, if a graph passes the vertical line test, we know that we have the graph of a function. And basically what we're saying here is for one input there's only one output. And we can see that for one x value there's only one y value. For one x value there's only one y value. Well, with the horizontal line test, if we take the graph of a relation, even the graph of a function, and we run that horizontal line through the graph, just like we have here, if we run that horizontal line through the graph of that relation, and it crosses in more than 2 points, then we do not have a one-to-one function. You'll notice here that f of a, this y, equals this y, but you'll notice that a does not equal b. So if you can run a horizontal line through the graph of your relation, and that horizontal line crosses in more than one spot, you don't have the graph of a one-to-one function. Now, it should be mentioned that a function is increasing throughout its domain. If that's the case, it's going to be one-to-one. There's a function that's increasing throughout its entire domain. And I can draw horizontal lines all day long through that. I will never cross that black line more than once. Same thing is true with a decreasing function. Here's a cubic function that's decreasing. Again, I can draw horizontal lines through that graph all day long, and I will only cross the graph one time. So here's a few functions to consider. Do we pass the horizontal line test? No, not one-to-one. Looks like some kind of absolute value function here. The absolute value of x plus 2 equal f of x. Once again, does it pass? Nope. Not one-to-one. Consider the graph of f of x equal x cubed plus 2x. Here you go again. Any horizontal line I want. Does it pass? No, it does not. Not one-to-one. So one thing I'd ask you to do for class discussion, come up with 2 functions that are one-to-one based on their graph and 2 that are not. And then be ready to share those in class, and you've got a couple homework problems here. So what's the big deal about a function being one-to-one? Well, if a function's not one-to-one, it can't have an inverse. And what's an inverse function? Well, an inverse function, boy, I'm glad you asked. An inverse function is, if we take a one-to-one function f with a domain of D and a range of R, a function g with a range with a domain of R and a range of D would be the inverse, provided the following condition is true. Y is the output of f of x if and only if x is the output of g of y. And it's got to be the case that your function is one-to-one for an inverse to exist. Alright? The thing about inverse functions. If I compose a function with its inverse, it's got to give an output of whatever the input is. Same thing here. If I compose a function with its inverse, the input's got to be the same as whatever the output is. And if a function has an inverse g, so if a function f has an inverse function g, we'll often denote this inverse function with an f superscript -1. Now, guys, in algebra we know that x to the -1 is the same as 1 over x. When we are using function notation here, f to the -1 is not 1 over f. Alright? Let me try to show you what we've been talking about here. Here's a graph you're probably going to see a lot from me in class. Here's my domain of f. Domain of f. Here's my range of f. I've got x. I've got a function. This takes me to f of x. Now, I've got another function. This is my inverse, f inverse. The range of the function is the domain of the inverse. Or I want you to think about this another way. This circle over here not only is the range of f, but it's the outputs of f. This circle, while it serves as the outputs of f, it serves as the inputs of f inverse. Now over here I've got the inputs of f, and this also serves as the range of f inverse, or the outputs of f inverse. Okay? And so keep those ideas in mind as we move along here. Use the graph of f along with the domain range relationship of f and f inverse to complete these statements. Alright, so here we go. Not sure what happened there. Notice that we look at part A here. Alright, as we look at part A, what we've got, the input of the inverse is 0. Alright, because here it's saying as x approaches 0, f inverse of x, the input of the inverse is 0, so the output is 3. And the reason for this is because the input of f is 3, so the output is 0. Alright, so we're thinking about here the input of the inverse. Maybe a picture. Here's my domain of f. Here's my range of f. Same way, we've got the input of f inverse, and we're saying that that input is 0. Well, where did 0 come from? 0 came from 3. So if the input of f inverse is 0, the output of f inverse is going to be 3. Okay? You say, "Ooh, Kev, that was a little confusing. What else can you do for me here?" Well, let's look at B. Let's look at B here. Now, notice on B it says as x approaches infinity, what's f inverse of x doing? So, again, the input of the inverse, if you will, and I'm going to put this in quotes because we can't really put infinity into a function, but the input of the inverse is approaching at least infinity. Now again, y is approaching infinity. Alright, well, where is y approaching infinity? If you follow my little dot here, as y is approaching infinity, what's x doing? Well, x is getting really, really close to 1. The output is 1. So as x approaches infinity, the output is approaching 1 of the inverse. Still a little unsure, still a little shaky? Well, let's look at part C here. Now you'll notice in part C, the input of the inverse is negative infinity. And again, I'm going to put the input of the inverse in quotes because we really can't input negative infinity into a function. But remember, these are the y's that live over here. Alright, so as y is approaching negative infinity, well, where's y approaching negative infinity? Right here, y, my y's are going down. And the output is approaching 1 again. Okay? So as my input to the inverse is approaching negative infinity, please remember this is in the y direction, my output is approaching 1. Now, here's where it gets a little bit interesting. We had talked earlier this semester about the fact that if we had, give myself a little more room to work here. Let's get a thinking bubble going here. Alright, if we had, let's say, x approach 2 from the right, this notation means x approaches 2 from the right. Well, in this case, when we look at D, x approaches negative 2 plus sign means as y approaches negative 2 from above. So here we go. Y is approaching, my y values are approaching negative 2 from above. Means as y approaches negative 2 from above, so instead of the right and left here, we're talking about above and below. As y approaches negative 2 from above, x is approaching positive infinity. See, as y comes at negative 2 from the top, x is going to positive infinity. And on part E here, as x approaches negative 2 from below. Now, we're writing x, but remember, folks, this is the input to an inverse function. Remember, the input to the inverse function, those are y values. So we're saying as x approaches negative 2 from below, but this really means as y, looking at this graph, as y approaches negative 2 from below, x is approaching, so here we go, we're approaching negative 2 from below, x is approaching negative infinity. Alright? So certainly, you've got some questions on that, be sure to bring them up. I know that's a little bit tricky, so feel free to ask questions if you want. There is a homework problem very similar to that. It'll give you a chance to kind of try that out. So if you have questions, certainly be sure to bring those up. Alright, let's see what we got here in our next example. What they're wanting us to do here, they want us to use the theorem on inverses to prove that f and g really are inverses of each other. And then we want to sketch both of these on the same coordinate plane. Alright, and so what we need to do here, just as a reminder, we will recall that f composed with its inverse should give me x, and the inverse composed with the function should give me x. And so let's see what happens here. F composed with g, f composed with g of x, well, this is 2 times 1/2 x minus 2 plus 4, which is x minus 4 plus 4, which gives me x. And let's consider g composed with f of x. So now we're going to take 1/2 times 2x plus 4 minus 2, this gives me x, plus 2 minus 2, this gives me x. So what we've just shown here, that g of f of x equals x, which is equal to f of g of x. Alright? And now we want to take a look at the graph of it. And you might say, well, why would I care to take a look at the graph of these? Well, functions that are inverses are symmetric with respect to the line y equal x. And so let's just take a minute here and go to our graphing calculator, and we're going to look at the graphs of these two functions, y equal 2x plus 4 and y equal 0.5x minus 2. And let's take a look at the graph y equal x. And I'll just do this on my standard viewing window here. And so I think you can see, here's my line y equal x, and you can see the symmetry that the two functions have. No proof there, but hopefully you can see that the relationship is true and that we've got the symmetry that we had hoped for. And so if you have questions there, certainly bring those into class. Now let's take a look here at our next example. And this is one where we've restricted the domain on g. Of course, we've had to do that, otherwise the function will become undefined. But if we look at f of g of x, what we're looking at is the square root of x minus 3 squared plus 3, which gives me x minus 3 plus 3, or x. And then g composed with f of x gives me, so what do we have here? Well, this is the square root of x squared plus 3 minus 3. Alright, and so notice what we did. We just put x squared plus 3 right in here for x. Alright, and so this gives me the square root of x squared, and of course square root of x squared over this domain is going to be x. And so we have shown that f of g of x equals x, which equals g of f of x. And again, if we want to graph these, we can pop open our calculator here, and we can go to y equals, let's see here, x squared plus 3, and then on y2 we can look at the square root of x minus 3. Still over the line, seeing the symmetry y equal x. And of course, when we look at this, we're ignoring this piece of the graph. I didn't restrict the domain here, but if we compare this piece of graph with this piece of graph, you can see the symmetry that we have there along the line y equal x. Now, I'll bet some of you are sitting there listening to this video going, well, this is pretty cool and stuff, but let's say I've got a function. And let's say I wanted to find the inverse to this function. How would I go about doing that? Well, boy, am I glad you asked. How do we go about finding the inverse to a function? Well, we've got it right here in our little note. Okay. And I guess I'm getting ahead of myself here a little bit. I thought we were going to get to find the inverse of this particular function, which we could. But it says here to determine the domain and the range for the inverse without actually finding the domain and the range. Now just recall, just a reminder, okay, that the domain of f is the range of f inverse, and that the range of f is the domain of f inverse. Well, my domain of f is a set of all reals except for 4, right? If I put 4 in for x, we've got a problem. Now, on the other hand here, we need to think about what the range of this function is going to be. And we know approximately what this function is going to be. It's going to have a vertical asymptote at 4. But it's also going to have, more importantly for our purposes here, we're going to have a horizontal asymptote at y equal 1. Alright? And now, are we ever going to cross that horizontal asymptote? Because we know all the other values are going to get hit. It's just, are we going to cross that y asymptote? I'm sorry, that horizontal asymptote. So we're going to set the equation of the horizontal asymptote equal to the equation of the function here. So x minus 4 equal x plus 2. Does negative 4 equal 2? No, it does not. And so we know our range of f is going to be all reals except 1. Well, based on what we know about the domain of f, the range of f inverse is all reals except for 4. And the domain of f inverse is all reals except for 1. Alright, so we can do all that just based off of our knowledge about the function itself. And so we've got a couple problems to work for class discussion and a couple problems to do for homework. So if you'd take a look at those, that'd be great. And now, what I was so excited to get to here a little bit ago, how do we find an inverse? How do we go about finding an inverse? And I'm so happy that you're sitting there asking yourself that question. And if you're not sitting there asking yourself that question, well, I hope you'll find this to be a somewhat interesting process anyway. So how do we go about finding the inverse? Well, the first thing we're going to do is we remember that y equals f of x. So we've got y equal 2x plus 3. Now what we're going to do here is we're going to interchange x and y. So x equal 2y plus 3, or x minus 3 equal 2y. And now we're solving for our new y. X minus 3 over 2 equals y, which is our inverse. And that's all there is to it, folks. We let f of x equal the y that it is, y equal 4x over x minus 2. We interchange the role of x and y, so x equals 4y over y minus 2. So we get x times y minus 2 equal 4y. xy minus 2x equal 4y. And now remember, we're solving for the new y. That means I need all the terms of the y in them on one side. So this is 4y minus xy. Negative 2x equals, I'm going to factor the y out, 4 minus x. So y, which is now my inverse, equals negative 2x over 4 minus x. Or another way we might write that is 2x over x minus 4 equals my inverse. We'll try to keep that top positive if at all possible. So if you have questions there, make sure you jot those down so that you can bring those up tomorrow. Now you'll notice here on example 13 that we've restricted the domain so that we're greater than or equal to 0. That'll be important here momentarily. Alright. So now we notice that x equals or x is greater than or equal to 0. We've got y equal 5x squared plus 2. So now x equals 5y squared plus 2. X minus 2 equals 5y squared. X minus 2 over 5 equals y squared. And so here we go, y, which is now my f inverse of x, equals the square root of x minus 2 over 5. Now, you say, well, don't we have to take a plus or minus here? Well, yes, but remember, x is restricted so that it's greater than or equal to 0. So y equal f inverse of x equals the square root of x minus 2 all over 5. Alright? Questions there? And then on this last, or on 14 here, example 14, y equals the cube root of x minus 4. Interchange x and y, so x equals the cube root of y minus 4. X plus 4 equals the cube root of y. And so y equals f inverse of x plus 4 quantity cubed. X plus 4 quantity cubed. And there's my inverse there. So we look at our next example here. And you'll notice I just made a little change there. Example 15 now will match with what you have in your notes. And so we're going to do some composing. Now before we finish off this last example here, we should note that if f of 2 equals 7, then f inverse of 7 equals 2. And likewise, if f of 4 equals 2, then f inverse of 2 would equal 4. And if g of 2 equals 5, then we know that g inverse of 5 equals 2. Alright, so when we look at part A here, g composed with f inverse of 7 becomes g composed with f inverse of 7. What is f inverse of 7? Well, let's see. F inverse of 7 is 2, and we know g of 2 is 5. If we look at B, f composed with g inverse of 5, this is going to be f composed with g inverse of 5. Let's see what we have here. G inverse of 5 is 2. F of 2 is 7. There we are. Looking at C, f inverse composed with g inverse of 5. Well, this becomes f inverse of g inverse of 5. Now this is f inverse g inverse of 5. G inverse of 5, that's 2. F inverse of 2, f inverse of 2, where are we at right here? F inverse of 2 is 4. And then we look at part D, g inverse composed with f inverse of 2. Well, this is g inverse of f inverse of 2. Now f inverse of 2, let's see, that's going to be 4. G inverse of 4 is, we don't know. We don't know. So we make that correction and we're ready to move on. And so this completes our notes for 4.1. Please work the class discussion, and if you have any questions at all, bring them along. We'll be happy to look at them.